The next thing I'm going to introduce to you is something called the follower, which is another tool for you to use. We start with our op amp, which we draw, right, as a triangle. We have our V input that is positive. We have our input that is negative. And we have our V out. Now, I'm not going to draw every time VCC plus and VCC minus and the ground. All right, I'm often just going to leave it at this point here. Now, untouched, right? Untouched, we said that if you were to build this, it would be something called a comparator. All right, that's what we talked about last time. Here's your next circuit. I'm going to extend it out like this. I'm going to extend it like this. I'm going to take a wire from here to here. And that is a follower. The next tool. And you're kind of, I'm getting a little bit like, what? Good. A bit of a what? What is this? To be clear though, I want to be, what this means is we're going to take a wire from this terminal here on the chip, and we will run it to this here. We're physically connecting, right, a wire from here to here. Right? What does that do? Let's look at this equation, right? V out, I'm just going to rewrite it, right, is equal to gain. I'm just going to write that as a G. It's a large number, times V plus minus V minus. Okay, that's the equation for an op amp. So we are relying on that equation with, I appreciate, the saturation limits. When you connect 2 points to each other, you're making their voltages the same. Right? This point here cannot be any different than this point as far, if this is at 1 volt, this is at 1 volt. It's the same point. So the way I would write that is I would say V plus is equal to V out. That is what this wire does. All right? Okay. So now I'm going to combine them and say V out is equal to G times V plus minus V out. Interesting. All right. And then I'm going to say, what's the best way to do things? I'm going to say V out minus G times V out is equal to G times V plus. And so this is going to be 1 minus G times V out is equal to G V plus. Make a mistake here? Made a mistake. What did I do? This is a plus. Okay. And then, like a final manipulation, V out is equal to V plus times G over 1 plus G. Multiplied by that. Okay. Now, I want you to understand that G is a very large number. Let's call it in practice 1,000,000 or 1,000,000,000. So I have a very large number over 1 plus a very large number. So I'm going to say that this is approximately equal to 1. Right? 1,000,000,000 over 1 plus 1,000,000,000 is not exactly 1, but it's very close to 1. If I reduce this to 1, I finish with this equation here. I'm going to write it here, which is V out is equal to V plus. This voltage, this is V minus here. Clear? So everything is right. V out is equal to V plus. By adding this wire here, right, I set V out equal to V minus, right? But because of this relationship here, right, I have V out is equal to V plus. Now, if you first look at this circuit, it seems like a whole lot of nothing. You start with V plus, and you end with V plus. So V plus is 1 volt, V out is 1 volt. If V plus is minus 1 volt, V plus is minus 1 volt. It's about as whole lot of nothing as you can get. The circuit does nothing, right? I mean, our comparator did something, right? It kind of flipped between something and minus, right? Voltage dividers do something, right? This circuit, if you think of it as an input-output, the output is just the input. So it doesn't do anything. Except this ends up being possibly the most useful circuit in biomedical instrumentation. So that needs to be explained. So useful that once you understand what this whole lot of nothing is about, you will not make an instrument without it. The hard part for me is not to explain to you what this circuit does. That's really easy, right? The hard, and by hard part I mean 10 minutes of discussion, is to explain to you where you're going to use it. All right? But mathematically, it's easy to build, easy to use. Why would you use it, right? V plus, V minus. Thank you. That fixes that. Okay. That fixes that. Okay. I want to go back to a description of the operation amplifier. I said first this, right? Rule number 1, right? If you want to call it that. And I said rule number 2, right? There's another rule that I didn't have to mention until now. But it is as important as the other ones. There is a current that is flowing this way into the amplifier, and a current flowing this way as well. Let's call this I plus, and let's call this I minus. Right? Some current that's flowing from the outside world into the op amp through these ports. The way these op amps are designed, I plus is equal to I minus is equal to 0, which means, in words, no current flows into the inputs, which is V plus and V minus of an op amp. That's this. This, and this are the 3 features of an op amp. And these are not simple to achieve, by the way, right? Every op amp, right, can have, I don't know, 1,000, maybe thousands of components inside of it in order to achieve this. And this is particularly critical. This is particularly critical, but why it matters is not yet apparent, right? Until I go back to the situation of the follower and what the follower does, right? Let's talk about combining circuits. And let's think about one circuit, which is our voltage divider. And we're just going to put values here. It doesn't matter. Let's say it's 10 volts, 1 ohm, and 1 ohm. Okay, that's a voltage divider. Now we have another voltage divider. I'm going to put it right next to it for a reason. Right? And in this voltage divider, we'll use different values. Let's call it 2 ohms and 1 ohm. All right. I can calculate what this voltage divider does using the voltage divider circuit, all right? So specifically, this voltage here, I'll call it V1. V1 is equal to 10 volts times 1 over 1 plus 1. I'm not going to simplify it, right? This is the voltage divider circuit for here. All right. What about this voltage divider circuit here? So I'm going to use my hand to block it. And I'm going to say, okay, I have V1. Here I have V2. What is V2 in terms of V1? Oh, I can use my voltage divider circuit, right? It's a voltage divider. I can say V2 is equal to V1 times 1 over 1 plus 2, whatever that is. So that's this voltage divider circuit, right? So in the final step, I will connect these. And now I want you to tell me what is V2 in terms of the input. And you might say, that's not a problem, because 10 volts becomes V1 like this, right? Or here, to make it even, right. And this is the next step. So what that would mean is you would say V2 is equal to, right, you would take this essentially and insert it into that, right? And so you would say it's 10 volts. I'll just simplify this as 1/2. Times 1/2 times this, right, which is 1/3, right? You solved one voltage divider, you solved another voltage divider, and then you just put the math together. Except you can't do that, right? The professor can put his hands like this and say, look at this. I did that for the Wheatstone Bridge, right? I said, look at this, look at that, and just treat it that way. You cannot. If you are in circuits class and you are given this circuit, you can't just start putting your hands over the parts that you like, it's like, what's that animal that sticks its head in the ground? Ostrich. I don't know if they really do that. They actually do that? All right. You can't do that, the circuit equivalent, which is putting your hands over the parts. No, you have to do things that they teach you in circuits class, right? With node voltage and current loops, and you remember all of that, right? Why would you need to do that? Well, you needed to do that because you can't just do this kind of thing, right? And so you have here the tool of the voltage divider, and you have here the tool of the voltage divider, but you can see that when we put these tools together, everything broke. It broke. And yet, I've deleted it now, but earlier I showed you how you can take comparator and remember I showed you that if you had one comparator and you had a light turn on, you could just add another one and another one? Why was it not breaking? How would this work? So the reason this doesn't work is because there is current flowing here and there's current flowing here. And so these circuits interact with one another. They interact with one another. This is what I would like. I would like a teleporter. This is what I would like to do. I would like a teleporter that looks at this voltage and teleports it to this position, and we'll do the same thing on the bottom, right? Right? But I want to focus here. It magically looks at this voltage, whatever it is. In this case, it was 5 volts. And it teleports 5 volts from here to here. But it doesn't actually make a connection. So therefore, I'm allowed to start over. And I can say, well, why not just go back and do the line? I mean, doesn't the line make this voltage the same as that voltage? It does make this voltage the same as that voltage, but it's no longer a teleportation. I've just made the connection. Oh, so you could say, well, then don't have a connection. Well, if they're not connected, how would 5 volts, how does this know that what this voltage is? Right? So I want to connect them, but I don't want to connect them. I want this voltage to equal this voltage without ever actually have connecting them. I want a voltage on one part of my circuit to teleport to another part of my circuit so I can do something else with it without having to connect it. And I want to make it clear now why you can't, and you say, what if I put a very big resistor? Well, if you have a very big resistor, then I have a change in voltage equal to IR. I can't put a very big resistor. If I put a very big resistor, this voltage and this voltage won't be the same. So I can't put a wire, I can't put, how do you teleport voltages? Right? How do you send a voltage from one place to another? The current here, we don't need, I'm going to just remove this little bend here because we're not using it. In this situation here, the current going in here, I plus, is 0. Right? I mean, it's also 0 here, but I'm worried about this one here. There's no current flowing into this op amp because that's one of the rules. So it's not just that V out is equal to V plus. It's that in a sense, they're not connected. I mean, they are obviously connected. Maybe I shouldn't even write that, all right? But it is a teleporter. Whatever voltage is here at this location will be teleported to this position here. But they're not actually connected. The ability to teleport voltages is of profound usefulness in biomedical engineering. We could go back to, now you could say, well, this is not an interesting example, right? Maybe in itself, I get that. But the way we would implement the teleporter here, so we could leave this here, and instead of drawing it this way, well, I'll use orange for the teleporting thing, I would insert an op amp. I would run this to the positive terminal of the op amp. Here is the output of the op amp. I hope that's clear. And then I would wire it in like that. That's the teleporter. And this teleporter, and by the way, I've never heard it called a teleporter anywhere else. That's what I think of it. Ends up being extremely useful for us. All right, as we move through the course, there will be certain situations where you're going to say, I wish I had a teleporter. And that's when you would use it. I'm not introducing this circuit as like something, like just to, what I mean? There's a particular reason, right, why I'm introducing this circuit as a very useful teleporter. I want to wrap up quickly with going back to the thing I erased, which is the circuit that will turn a light on and off depending on the temperature. So I'll redraw it here. Here's our E. Here's our R. I'll just use an R fixed. This is our R, let's call it temperature. So put a square around it. And then I said you can take this line here and draw this next thing purple, and you could bring it to a comparator. Right? And use that to turn on a light relative to some voltage, right? I'll call this VR1 for VREF, all right? And here's the LED, and this is our comparator. All right, I've gone through that quickly because I went through it slowly before. I've just quickly redrawn it. Now you can say, wait a second. This has now been attached to this. Right? Can't just attach stuff. You bring circuits together, you have to figure out how the whole circuit works together. Except, how much current is flowing down this line here? It's 0. There's no current being drawn this way because there's no current going into the comparator. I didn't mess it up. As far as this circuit is concerned, it's not here. This doesn't exist because there's no taxis, right? There's no current going down this line here. So I'm allowed to use voltage divider here. It's good. And then, you see, do this. And then I said, you can add another one. So we'll go here, draw it carefully at an angle, and you can go ahead and add another comparator. And now there's going to be another voltage here, but we'll call this VR2. And here we have our LED number 2. And I said, yeah, just add another one. Oh, well, what do you mean? You have to solve 1, 2, 3. You have to solve it all together, right? Node voltage and all that. Except, once again, this current is 0. That's why you're getting this for free. That's why it's so easy. And that's why you can add another one and another one. You can't normally do, yes?
When we were solving for op-amps in the previous class, we said that V plus and V minus, we would consider that to be the same.
Correct.
So
So your question is, when you were solving other op-amps, you were saying that V plus and V minus are the same. And I have not introduced that concept yet because we haven't needed it.
so is the
Oh, sorry, why is V plus and V plus, as we will learn next class, V plus and V minus are the same when the op-amp has a negative loop. In the case of a comparator, which is, by the way, the only circuit where we don't do this, there is no wire, negative feedback, it will also be called, going from the output to the negative. So when I first wrote the equation for an op-amp, I didn't say V plus equals V minus because you didn't necessarily have negative feedback. A comparator, V plus does not equal V minus because you do not have negative feedback. For this circuit, it is true, actually, that V plus is equal to V minus. And what you're thinking ahead at is circuits that you've seen called inverting amplifiers and things like that. We will get to those. And they're, as you will find out, they're just Ohm's law plus this. Okay? That's it. We're not going to go beyond Ohm's law. But we didn't need it until now. Yeah. But it's a very good point. So in this case, certainly V plus is not V minus. And so what you see now is what you've gotten. We don't use op-amps because it makes her life hard. All right? We use op-amps because it makes her life easy. You want to go on in instrumentation and in this course and try to do things without op-amps? By all means. I don't even know how you're going to start solving these problems. All right? Op-amps are made to be, it's weird to say, but I gotta say, op-amps are made to be useful and easy. So initially when I put up the op-amp and you're kind of like, oh, I remember this from circuits, that's not how it's going to be here. Here there are things that are solving problems, all right?